Welcome this evening to the Wilson Museum, both in person and those of us who are joining virtually. I'm Julia Gray, I'm the executive director here, and I want to thank you for joining us here in Castine, the homeland of the Penobscot Nation and their Wabanaki relations, and wherever you are zooming in from. This evening, we are joined by Dr. Paul Mayewski. Mayewski? Mayewski. No, I'm happy to be corrected. Director of the Climate Change Institute at the University of Maine, and an internationally acclaimed glaciologist, climate scientist, polar explorer who's led over 60 expeditions throughout the remotest polar and high elevation reaches of our planet. As one place put it, the three poles of our planet, the Arctic, Antarctica, and Mount Everest. He has more than 475 scientific publications and 2 popular books, The Ice Chronicles and Journey into Climate, and appears regularly on national and international media channels and on TV shows like Nova and Showtime's The Years of Living Dangerously. Paul and his wife, Lynn, on a more personal note, live here on the Blue Hill Peninsula and are longtime members of the Wilson Museum. Lynn's fiber art can be seen as part of our summer art show here at the Wilson Museum on a regular basis. This evening, Dr. Mayewski is going to be sharing insights from his award-winning research and extensive experiences in the Arctic, focusing on significant impact of this apparently isolated, not really, as we'll learn, part of the globe has on the rest of the world, especially as it is warming at a rate of 2 to 3 times the rest of the planet. I want a special shout out to Bangor Savings Bank, whose support makes this Connecting to Collections program series possible, and invite you to come back once we open up in the spring.
Oh, see, I don't.
So welcome and thank you.
Thank you very much. Well, thank you so much for coming. It's a wonderful opportunity, and the best part is to get to see some friends that we don't get to see that often. So thank you for coming, and all of you who are on the screen, wherever you are in there. The Arctic obviously has been in the news quite a bit lately. And because you have an Arctic series, I think that's been going on. Maybe I'm number 3 or number 4. Number 4. I'll focus primarily on the Arctic today. I will take you to a couple of other parts of the world because I'm going to tell this Arctic story in a semi-personal way. There's some science in it, obviously, but in a semi-personal way about how the teams that I've been leading for many years actually ended up doing some of the things. Sort of an ugly second slide, but I did this on purpose to remind myself. What I'm going to do is sort of ask some questions and then try to answer them. But there are 2 basic questions in the beginning that I'll start with. And the first is, how do we know that the climate is changing? I'm going to guess that everybody here probably believes that the climate is changing, but we really do know it, and we know it for several reasons. Number one, the Intergovernmental Panel on Climate Change, IPCC, has for many years on providing reports that come out every 3 or 4 or 5 years. This is made up of 145 countries, many people. They synthesize tons and tons of information, and they come up with the least common denominator understanding of what's going on in the system. So if they say that the climate is changing, and in particular, if they say that it's a consequence of human source greenhouse gas rise, then that's about as conservative an approach as you can take. I'll push a little bit farther than that, but I think it's very important to understand that 99% of climate scientists actually do believe this is real. There are also reports that come out by, amongst other groups, by NOAA. One's called the Arctic Report Card. And from the Arctic Report Card, you can tell on a yearly basis what some of the big things are that are happening. And you've already heard that the Arctic is warming at least 2 to 3 times that of the rest of the globe. And I'll show you where that's actually happening and why it's important. But there's another way of actually finding out that the climate has been changing. And it has no potential political, scientific bias, anything. It's ice. Ice doesn't lie. When it gets warm, ice melts and glaciers get smaller. So it's in effect the primary sentinel for climate change. And we have been able to observe this, people in the institute that I direct, which is a rather large institute, one of the oldest in the world, for many years, and from many different parts of the world. But what you see here in white and blue are the places on the planet where ice exists. The important thing about this is not only are glaciers a sentinel for how the climate's been changing, and it is very, very clear that these glaciers are disappearing fast. I'll give you one quick example in a moment. But these glaciers contain 2% of all of the water on Earth and 70% of all the fresh water on Earth. So all of a sudden, these glaciers become a very important resource, particularly for people in mountain areas for their livelihood, for agriculture, for hydropower, a variety of things. So again, my teams and I have been doing this for more than 50 years. Let me show you one of the first things that we learned. In my early expeditions in Antarctica, I've crossed the Antarctic ice sheet many times. We ended up going into a new region, the red circled area. It's called Northern Victoria Land. Up to that point, even having been there several times, I learned, and I was a graduate student primarily, I learned that the Antarctic was a timeless place. The extent of the ice never changes, no matter what you do and what year you come back, it's always the same. But on this very first exploration of Northern Victoria Land, a rather large area, we started to see that the glaciers that are in the mountains, the Antarctic ice sheet is 3,000 feet thick on average. But when the mountains are high enough, there are actually glaciers in the mountains. We began to realize that these glaciers were actually getting smaller. We didn't know when. We thought it might be in the last few hundred years, but even there was no expectation that these glaciers would even change their shape in 100 years. It was a big shock, actually, and we wrote a few papers on that. And then fast forward, and a lot of things in between related to glaciers. Fast forward to 2019, I was asked by the National Geographic and Rolex to lead the Mount Everest expedition. And we had hoped that our team would get to the top and be able to do various things. It was the year when there was those tremendous crowds. But what our team was able to do, and this is my graduate student in the middle, with a drill, was to drill on the highest glacier in the world and recover the highest ice core ever recovered. So you can see in the lower corner, it's 26,500 feet high. It's in the beginning of what's called the death zone that starts at about 8,000 meters. Then you have another 800 plus meters to get to the top. And the most impressive thing that came out of that was that as soon as he started drilling that, realized that there wasn't snow, there wasn't compacted snow, which is called firn, but it was immediately ice. So the samples went back to the lab. We have a colleague in Switzerland who does radiocarbon dating of ice, and the surface of the ice turns out to be 2,000 years old. That means that 2,000 years of ice was missing from the highest glacier on Earth. And therefore, I mean, we know that the Arctic is warming. We know that the edges of the Antarctic are warming. We know that the ocean is warming. Even the highest part of our planet is actually beginning to change as a consequence of greenhouse gases. So we have a tremendous amount of science and glaciers to tell that this is happening. And the only other basic question, although I'll use this format a little bit, but I won't shock you with the red every time, is why is atmospheric circulation important? When I talk about atmospheric circulation, I'm talking about the winds that we obviously are subjected to from south, north, et cetera. And for the part of the story that I'm going to talk about related to atmospheric circulation, I have to go back to one of our early expeditions in the Himalayas. We went to a place that had only been visited once before. It was about 100 years earlier, about 80 years earlier, by a very famous climber, Fanny Bullock Workman. She did a lot of climbing in the Himalayas. She took pictures of where she went. And at the time that we were going into, this is the Indian Himalayas, we weren't allowed to have maps. We weren't allowed to have any form of communication. So to find it, even to find a place to go, I had to basically use the books that she used. It eventually, these are 3 ice falls, each 500 feet high. It took us 6 weeks by the time we got to the top of that plateau, close to 20,000 feet, where we were going to drill. But the most important thing that happened, which was a surprise, was that we saw snowfall coming from the north, which is the Tibetan Plateau, and snowfall coming from the south, which is the Indo-Gangetic Plain. And typically you don't necessarily see snow coming from 2 directions, but that was very important because that gave us the opportunity to test what at the time, which is the late 70s, or early 80s, was the idea that air masses actually have chemical fingerprints. So The Tibetan air masses should, if there is a fingerprint, have a cold fingerprint. They should be very dusty. It's a high plateau, more than 10,000 feet. And air masses that come from India will have come from the ocean, should have sea salt, they should have agricultural properties. And we were particularly interested in understanding this because what I just described, when air masses come from the north into the Himalayas and then from the south, this is the South Asian monsoon. And the water masses that come, the air masses that come from the south, the Bay of Bengal and the Indian Ocean, transport moisture, which helps the glaciers grow. But more importantly, that basically dominates the livelihood of the people who live in that area. Too strong a summer monsoon, and there is too much rain, people die from flooding, too little, the opposite. So as it turned out, the samples that we collected went from 20,000 feet down to 10,000 feet. Our camp was at 20,000 feet. We collected fresh snow, climbed back up to camp for the evening, took the samples back to the lab, analyzed them, and that's exactly what they showed. They showed sea salt coming from the south, cold dust coming from the north, and now, well, as of probably about the late 90s, you begin to see animations like this. This one actually is from 2006. These are actual satellite images that have been put together in an animation. And the clouds, which are identifiable, obviously, because they're a little whitish, have been colorized by NASA. And what they did was actually show what we years ago were able to explain to ourselves. It isn't that nobody else knew about it, where these air masses came from and be able to track them. The orange, which is the most spectacular thing on here, that's Saharan dust making its way from the Sahara as it goes eastward, westward, sorry, with the winds that go from east to west. And you can see that that orange dust makes it right into southeastern United States. That orange dust also makes it into the Amazon. It's got a lot of iron in it, which is why it's red and fertilizes the Amazon. If you go to the Southern Ocean, that bluish is supposed to give you the impression of sea salt, tremendous, obviously large ocean. The green is biomass, the signal for biomass burning. And then as you go into the northern hemisphere, you see those white swirls, and particularly, I'll get away for a second, the Icelandic low right up there, which is what brings us our storms. That's not only blue because it has sea salt, but it also has a little bit of whitish in it. And that whitish is supposed to represent pollution because the northern hemisphere is so polluted. So this is an amazing dramatization of exactly what we then use to track air masses and go back through time. So why do we care about air masses? Forget about why we care about them. Well, we care about air masses because they transport heat, they transport moisture, they transport pollutants, and they also have an impact on surface ocean currents. So if you understand where air masses go, if we always knew when the air was going to come from the south, from here for the next 10 years, we would be in much better shape than we are now. We'd know that in general it would be warmer. If you put all of these different air mass events together, drill down into a glacier, you get an ice core and you can go back literally storm by storm, decades, hundreds of years. And in fact, now we've gone back a couple of million years. And these red dots show you where my teams have done our drilling in the last roughly 50 years. The important thing about reconstructing a record of air mass behavior is, I showed you the animations, but you can also monitor past temperature, past precipitation, changes in solar activity, agricultural activity, mining activity, volcanic events, productivity in the ocean, productivity on land. It goes on and on and on. There are about 100 plus measurements that you can drill. So what does this have to do with Greenland? This thinking about air masses was really becoming very prominent in our minds about the middle 80s with respect to ice cores. And then we connected with EPA. And at that time, if you remember, we weren't talking about greenhouse gas warming, we were talking about acid rain. And there was a big discussion. Was acid rain created by humans or was it not created by humans? And we suggested that if we went to that star area there in southern Greenland and drilled an ice core, that we would be able to show by comparison with known emission records of sulfur and nitrogen, which are the two primary components of acid rain, whether or not it was elevated along with the emission record, and in fact, was it flatter prior to that? But to do it, we needed to go and drill this ice core, which we went down probably 400 or 500 feet. We couldn't use any sort of fuel because we would be contaminating the sample. So it was one of the first times that solar panels were actually used for drilling. And what we were able to do, you see a drill here, and the people dressed in the cleaner clothes are the ones who are actually sampling the ice, because even just touching it was you have enough sodium chloride in the sweat in your fingers to offset the record. And what we were able to prove, most importantly, was that yes, we were in fact the primary producers of the elevated levels of sulfuric and nitric acid in the atmosphere. Sulfuric acid primarily as a consequence of the beginning of the Industrial Revolution, nitrogen compounds pretty much when we start to have a lot of automobiles. And then as we went back more often and sampled even younger, because the first sampling was in the mid-'80s, we found out that the Clean Air Act was actually working, that the levels were beginning to flatten out. And this, in my opinion, is a very important thing to understand, that these Clean Air Acts can be demonstrated to work. So with this understanding of what you could do with an ice core, we thought it would be great if we could find a place where we could get the longest possible ice core record in the Northern Hemisphere, and that turns out to be Greenland. So I spent a lot of time with my team. This is a big vehicle that we had. We had snowmobiles, we had skis, all sorts of things. And we went back and forth across Greenland in order to find a good place where we could get the thickest record, which would be in the summit of Greenland. And I ended up being in charge of a program for the National Science Foundation, which included 25 US institutions, all dedicated to recovering this record, which we did down to bedrock. We went about 10,000 feet. It took us about 18 months in the field, spread over 5 years. And we were able to recover year by year a reconstruction of past climate for the last 110,000 years. So that covers what's called the interglacial, which is our modern day, roughly modern day time period of climate, last 11,500 years, and the preceding 90,000 years, which is basically a time when glaciers are more expansive. So back to these questions. So the question is, how do atmospheric circulation patterns change when, for example, it gets warmer? How fast can climate change? And I'll show you why that's important. And how small a change in climate is important. And this all comes right back. Not only was this drilled in Greenland, but it ended up telling us an awful lot about Greenland and how Greenland would impact the Northern Hemisphere in the future. So first of all, what you're seeing on the left side is a reconstruction of what the Arctic looks like under very cold conditions, a lot of ice, a lot of snow, all to the white. The bottom is a warmer Arctic, which is what we have experienced for the last 10 or 11,000 years. Not the warmest Arctic, but a warm Arctic. And one of the biggest things that changed that we saw in this record was that when the Arctic was very cold, the jet stream, this air mass that primarily goes from west to east, allowing you to fly faster from California to Boston, tended to move along lines of latitude. And as the warming occurred, and I'll explain a little bit more about this as we go along, as we begin to lose ice, the shape of the jet stream starts to become much more embayed. So this was the big general idea that we got. But as we started to cut the samples in the field, in this basically lab that we built into the glacier, and section them and send them to the various universities, including the one that I was involved with, and then did the analysis, which took quite a while, we were able to do the following. We were able to demonstrate how fast climate could change. And from this picture in the upper left, this is a generalized understanding of what people thought was the way the climate operated until about 1992, when we came out with our findings. And this is roughly the last 110, 120,000 years. And you can certainly see that there are times when the climate appears to move rather fast, but in fact, when you think about 120,000 years, there are not a lot of wiggles on this thing. And in truth, the climate never operates much faster based on this thinking than maybe hundreds of years, or even in some cases, thousands of years at a time. Why does that matter? It matters because if you pump more greenhouse gases, which it has been demonstrated since the late 1800s, can warm the planet. If climate responds that slowly, then it probably doesn't really matter. However, that's not the answer. This is the answer. There were a lot of wiggles, and in fact, when the climate changed, without going into a lot of detail, or when you see these wiggles, I should say, there were massive shifts in storm frequency, precipitation, temperature. Most importantly, some of these shifts occurred in less than 2 years, which means that the climate can operate faster than a political cycle and actually do something in the process. And it can be sustained for many decades. So this was the early 1990s. We appeared in the newspapers for 2 or 3 years after that. There were some nice documentaries done, interviews, but the organization that actually figured out, well, did a better job of advertising than we did or anybody else was Hollywood. The Day After Tomorrow in 2004, when of course, it's all patterned after our work. There's a glaciologist there drilling an ice core who says, by looking at the ice in the field, which is quite remarkable, that in the next couple of weeks, the Northern Hemisphere will be covered with this really thick ice. Of course, they got it going in the wrong direction for what's happening right now. But the point is that they got it, they really figured it out. They understood that something could really happen fast. And they asked the question, where will you be? This comes directly from their advertising, which I'll mention as we go on a little bit. So the next question that we asked ourselves that we were able to answer is, okay, so the climate can change. What if it only changes 1 degree centigrade, which is a little bit more than 1.5 Fahrenheit? If we change the temperature of this room in 1 degree centigrade, nobody would notice. Could that possibly have an effect? And the answer is that if you take a look at the abrupt climate change events that we identified throughout the entire 110,000 years, but in particular during the last 11,500 years, which is the time similar climate-wise to the way we live today, you see that major changes in civilization follow these. The most prominent is 4,200 years ago, which is the collapse of the Mesopotamian Empire in modern-day Syria and Iraq. And that's a time when they built large cities, but unfortunately, the precipitation that fed those cities and provided them with water no longer appeared on a regular basis. Within 2 to 10 years, they completely abandoned all of the places that they lived. The same thing happened 900 AD in the Mayan Empire. So if this is an ice core that comes from Greenland. Why in the world would we think that this had any impact on Mesopotamia or any other place? But you'll see actually in a little bit how it does. And then in 1000 AD, when the climate was a little milder, probably about as mild as today, the Norse moved from Iceland to Greenland, settled there, but by 400 years later, they had completely disappeared because they never adopted Inuit culture. And they depended on vessels that could go from Iceland to Greenland. And by 1400, plus or minus a couple of years in there, it got colder again and the sea ice expanded. And that's the beginning of what's called the Little Ice Age. So civilizations can collapse or rise as a consequence of small changes in climate, because these changes are really nothing more than about 1 degree centigrade at most. And this one is perhaps the most interesting. 4,200 years ago, modern day Syria and Iraq, that's part of the underpinning for all of the fact that so many people in those countries wanted to see something else happen because they were subsistence farmers and they were no longer able to do that. So that's really the sort of the science that has come out of what we've done. But even saying that there might be an abrupt climate change, despite the fact that it got into the papers and into Hollywood, it really didn't have that much impact on people. In general, people have been pretty disinterested in the Arctic, but they shouldn't be for 2 big reasons. The Arctic, as opposed to the Antarctic, is much more sensitive in its potential response to climate. Even 1 degree centigrade makes a very big difference in the Arctic. The Arctic, of course, is primarily the Greenland ice sheet, which is 1/10 of the size of the Antarctic ice sheet. But it's just an island, the largest island in the world, but nevertheless, it's just an island. And all of the ice is frozen sea ice, with a few glaciers throughout Canada and other places. But because it is the northern regions, the North Pole area, is really just sea ice, which is typically only 3 to 10 feet thick, as opposed to the Antarctic, where the average thickness is 10,000 feet. It's much, much more prone to potential change, as you'll see in a moment. The other reason why we in Maine should care about the Arctic is that we're only 1,400 miles away from South Greenland, but we're 2,700 miles away from Washington State or whatever. So we're much closer to Greenland. And in fact, those of you who are familiar with Portland probably know that Imskip, which is an Icelandic shipping company, has actually moved all of its operation up to Portland. And the exchange between Portland and Iceland and Greenland and Scandinavia is only going to get larger. So what's the big thing that has suddenly made us much more interested in the Arctic? It's the rise in greenhouse gases because of their heating effect. And this is a record that comes from an ice core, not ours, but it goes back 800,000 years. And it shows you the range of variability in red of CO2, which is only one of the greenhouse gases. And you can see that it stayed within a certain range for 800,000 years. Until just a few decades ago, we see this dramatic rise of about 1.5 times greater than any of the natural variability of the last 800,000 years. But what is, in my opinion, even more important, and what gives greenhouse gas rise the ability to create an abrupt climate change and to do some things that make the Arctic very important to us, is that it's increased 100 times faster than any other time in the last 800,000 years. So let's take a look at what global warming thus far really looks like. The implication is global warming means that the entire globe warms. And the answer is yes, it eventually will. And we're certainly on our way to do that. But the warming thus far, if you take a look at take a look at the last 20 or 30 years prior to the previous 20 or 30 years, this is the distribution of that warming. First, notice that there are places where there's actually a little bit of cooling. This is in the Southern Ocean. This is because the winds actually have increased around Antarctica. I won't go into the details, but as they increase, they drag relatively warm surface water, and cold subsurface water comes up. But what's more important is that most of the warming, that's sort of orangish, is in the northern continents. And the greatest warming, obviously, is up in the Arctic. So let's focus in for a specific time period, which turns out to be 2007, 2007 or so to 2014. And within that time period of about, 2010 to 2014, within that period of about 5 years, temperatures increased in the Russian Arctic, where you see the reddest area, by up to 5 degrees centigrade, which is 8 degrees Fahrenheit. This is an abrupt climate change in terms of temperature. And we have pretty much stayed in this state, in this region, ever since then. So what does that mean? Well, first of all, it's the biggest change that has occurred in the modern era. It is an abrupt climate change, and it's an abrupt climate change based on what we found in the past, because of the rate of change and because of the magnitude of the change. The magnitude of this change is as great, and the rate is as fast as the transition between the last vestiges of the Ice Age, 11,500 years ago, and modern climate. So we have experienced something very, very new. The only difference is at that time, since there was much greater ice coverage, that the abrupt change was felt over a much larger area. So why is the Eastern Arctic, or the Arctic in general, so sensitive? Well, it turns out that sea ice, and you see an animation of sea ice going through the months here, ultimately covers about 30% of of the continental regions. And it goes back and forth, obviously, on a monthly basis. Every year is not exactly the same, but obviously in the Northern Hemisphere, there's much more sea ice cover in the winter. And on the left side, you see what the sea ice cover was in September, just as it's really beginning to build up in 1980. And as of about late 90s, 2000, people said, it's possible with greenhouse gas rise that sea ice extent in the Arctic will decrease sometime in the future. The first suggestion was that it would decrease dramatically by 2040. This is in the early 2000s, late 1990s. And then the next estimate was that it would be 2025, and that was around 2012. And then by 2010 to 16, it was beginning to change. That's when the abrupt climate change almost occurs, and you begin to see a situation that looks much more like this. So even the models could not predict that this would happen because there was no analog. There was in the ice core record, but not in the kinds of records that you use for modeling. So the question now is, why does sea ice play such an important role, or snow for that matter? And that's because when you have snow cover or sea ice cover in a place like the Arctic Ocean on the left side, if it's very white, it reflects 100% of the incoming radiation. And once you remove it, the ocean is dark, it absorbs the radiation, but it is already warm and it gives off heat. Under the max ice cover situation, that heat's all trapped under the ice. It can't get back out again when you remove it. And that's why you have 2 to 3 times increase in temperature relative to global temperature in the Arctic. So what does this have to do with the rest of the Northern Hemisphere? What happens during these periods when or I shouldn't say periods, but what has begun to happen since this abrupt climate change in the Arctic is the Arctic is not as cold as it used to be. And if the Arctic is not as cold as it used to be, then the temperature difference between the Arctic, normally very cold, and the mid-latitudes begins to flatten out. When the gradient is very, very steep, the temperature difference is very, very steep. You get these more west to east patterns without going into a lot of detail. And when the gradient is weaker, you begin to get these very large embayments. These large embayments bring cold and air masses together, not just along a latitudinal line, but along all of the embayment shapes. And as a consequence, it creates tremendous instability. That's when you get storms. And the net result is you're transporting heat, intensifying storms, having drought in some places, floods in others, and fires in others. So let me show you 2 dramatic examples of how this is operated, this embayment in the jet stream. This is this comes from software that we've developed that's publicly available. Starting at about 2014, 2015, not every day of the winter, but some days during the winter, very, very close to Christmas time. This is December 30th, when it's absolutely dark at the North Pole, obviously very, very cold. The embayments of the jet stream, this orange pattern that you see, allows cold air to push farther south over the Western Atlantic and allows warm air to go all the way to the North Pole, putting the North Pole above freezing for some small number of days, but that's not happened before. So it's really quite dramatic. And here's the other side of the picture. This was all of us, December 23rd of last year, or this just a couple of months ago. And there's that dramatic cold wave that came down with all of the temperatures. And you can see that's sort of showing you this, focusing in on an even more dramatic one. And this broke tons and tons of records. So next question is, what are the impacts of of climate change in the Arctic and worldwide? So to do this, we can basically take a look at, I'll focus more on the Arctic, but I'll talk a little bit about globally too. There are 4 big categories, which I'll talk about fairly briefly. One of them is impact of climate change on health and resource depletion. And all of those examples in there are things that we work on in our institute, but I'm only going to focus on one, just pollutants. And remember that in order to, one of the early things that we did, and we're not the only people in the world who did it, was to start looking at pollutants. So let me go back and tell a story from earlier years about how we got involved in pollutants and what a surprise it was to us. After we finished the drilling in Greenland to work on the acid rain question, we decided that we needed to find out what is the cleanest place on the planet and what are the absolutely natural levels of various elements. For example, lead, mercury, cadmium, which actually is one of the causes of autism in small children. What's a safe level? Safe level ought to be what you find in the natural system. So where would you go to get a baseline for what the natural system would be? The place that you would go would be Antarctica. It's the most remote from the industrialized world. And it has its own, because it's high, it's tons of ice, it stays cold, it pushes air masses off all the time. It ought to be one of the most pristine places in the world. And in truth, it is, but not exactly. So as I've traversed Antarctica quite a few times too. This is one of our camps moving across Antarctica. This one turns out to be a couple hundred miles from the South Pole. Mean annual temperature here, not the mean annual temperature here is -52 when we're here. So we camped along our traverse routes and then skied away from there because we might have polluted the area. And then finally, maybe 15 miles away, put on clean suits and collected some surface snow to bring back. But we also realized we needed to go back in time a little bit more. So we dug a snow pit at that very same location, -52 degrees centigrade. And this is a 6-meter snow pit. Took us 4 days to dig it and sample every single centimeter all the way down. And as we did that, we were able to go back year by year, about 100 years. So the snow accumulation in this area is very, very low. We discovered a whole bunch of things. I'll just mention one because it tells you how far air masses can travel. And this was, nobody actually knew because you needed to find a tracer. So we found the Chernobyl nuclear accident radioactivity at that site, not far from the South Pole. And Chernobyl was at 51 degrees north, and we were pretty close to 90 degrees south. The only way that can happen is to get very high up into the atmosphere and be transported there. We found a bunch of other things in that snow pit, but we became so intrigued by that that I put together a collection of, turned out to be 21 countries who all dedicated, Antarctica is a big place. It's 1.5 times the size of the United States. It's not a place that you can just sort of get around by yourself. And we did a whole series of traverses. These are the US traverses in red, but a lot of the black dots are done by other countries. And we came up with a system, a tractor, pulling fuel, which we exchanged for ice cores as we drilled the ice cores, and then places to eat, and did a whole series of different experiments. And the pollution side of this, can be quickly summarized this way. We not only found Chernobyl making its way to the South Pole, but we found uranium coming from open pit mining of uranium in Australia all the way to Antarctica. And we also found copper, which is the biggest thing that's open pit mined in particularly Chile, making its way into Antarctica too. Since then, we've been working in a variety of other places. We've moved to we work in all these places pretty much every year, but we've been focusing also in South America lately. This is an ice core from this particular one we drilled in Chile. And we've also been working in Europe, looking at how pollution has changed over time. There we found several interesting things, but the most interesting thing that has to do with pollution was the fact that there was one time in the 2,000-year record that we recovered from the Swiss-Italian Alps that the levels of lead, and lead's very important, it has impact on cardiac health and also on neurological health. And it turns out that during the Black Death, when half the population of Europe died and nobody was mining, nobody was smelting metals, the levels of lead dropped down to almost zero. That tells you that that's a natural level of lead. And that's very important because understanding what the natural levels are is the way we determine what the safety levels are, because obviously we'd like this to be as close to natural as possible. We've been doing the same thing in the Southern Ocean, been chartering. Anybody knows Skip Novak, probably the most famous blue water sailor in the world. He owns this boat. We go with him, and we've done several thousand miles in the Southern Ocean, visiting islands, drilling short ice cores, and also collecting snow and ice samples. And the net result of all of this has been that what we have done to the atmosphere, this is a record that is plots on the right go back 5,000 years. If I actually would have put this in proper perspective, I should have the full range of the Earth, the length of Earth history. In the last 150 years, we have absolutely changed the chemistry of the atmosphere that we live in. And all this list of pollutants, toxic substances, is what we put into the atmosphere. What does this have to do with greenhouse gases? Even if you don't care about warming or don't believe in warming, and I'm not saying that's anybody here, but for people, I lecture in a lot of places. But if you don't care about greenhouse gas rise, guess what? All of these things go along with greenhouse gases. And if you want to live in a healthy environment, you should get rid of these things. And in the process, you get rid of greenhouse gases. Air quality is a very big thing. 1 in 10 deaths worldwide are attributed to bad air pollution. Water quality is probably worse, but it's hard to get numbers for that. And that results in about 7 million premature deaths per year. So all of the chemistry that we have been looking at for these many years, and other people too, has been deposited in Greenland, Antarctica, the Himalayas, the Andes, and Europe, and it's all and Alaska. It's all obviously been melting. So what happens when it all begins to melt? Is it going to impact the chemistry of the water where we live? And first of all, let's take a look at how much melting is going on. This is the Greenland ice sheet. It melted. This is the situation in 1992. That red star is where we did our drilling, our deep drilling. And the pink shows you where the melt was in 1992, not all year long, but during the height of the summer season. By 2002, the pink has gotten much larger. And then by 2021, although this one has different colors, the blue is now supposed to show you the melt. And by 2021, even where we worked on the highest elevation of Greenland at about 11,000 feet, there's melting that occurs up there. So there's no doubt that the Greenland ice sheet is melting. And in particular at lower elevations, and particular in the southwestern part. So again, we rented another sailboat last summer. We went in and out of some of the embayments along the Greenland coast, and we collected samples of water from many different places. This was just, we managed to do that this last season. These are just the measurements for lead. We did many other measurements, and lo and behold, the lead levels, once you get into the very blood red, 2,700 to 18,000 nanograms per liter, you're well into unhealthy levels of lead. So there's lead coming out of the meltwater from the Greenland ice sheet, and a variety of other things are going on. So there's no doubt at all that Greenland the warming of Greenland is impacting our health because of not only pollution, but also because of how it's been changing atmospheric circulation. So let's take a look at the second big thing. We don't study all of these. We do study some of them, in particular the one in yellow, energy and economy. Let's take a look at how this is focused on just the Arctic. How has warming impacted the economy, fisheries, agriculture, shipping in the Arctic? And this is a beautiful representation that the Intergovernmental Panel on Climate Change does. They take hundreds of papers and put them together and produce a beautiful figure like this. And what this shows you is anything that's in blue in the top is a positive effect. They consider opening up of shipping a positive thing. You can debate whether it is, but nevertheless. And then the reddish one are negative effects. So the bottom line is that as the sea ice has decreased, not only has the yearly sea ice decreased, but the multi-annual sea ice, which used to be much more extensive than it is now, which was a habitat for many organisms, has decreased dramatically. It also has another effect. When that multi-year sea ice, which is much thicker than the annual sea ice, is there and it's disappearing, it creates an anchor for the annual sea ice, allowing it to be larger. In addition, there has been acidification of the water as a consequence of not only greenhouse gases getting into the water, CO2 creating carbonic acid, but also the stuff that's coming out of the glaciers themselves. There's a change in the stratification of the water because you're now allowing fresh cold water to come into the Arctic regions, and as a consequence, because it's very light, it stays up there, it changes the normal turnover. And overall ocean warming has had a tremendous impact, as it has in Maine, on the lobster industry. So the overall impacts for the Arctic have been very dramatic. That was on the ocean. The impacts of warming on land, again, a beautiful graphic from the Intergovernmental Panel on Climate Change, demonstrates, without going into detail, that permafrost is thawing at a greater rate than before. Lake ice is present for shorter time periods, seasonal snow, less so, river discharges increasing, and you can read the rest. There are tremendous changes. And one of them comes out in this next graphic, which also comes from the same group. And this is the infrastructure damage to roads, buildings, airports, railroads, et cetera. And there are two different approaches. One is under an emission history, which will begin to flatten out. The other one is under an emission history in which CO2 levels go up. But the bottom line is that these are in millions of dollars. And there are tons of take-home messages. If you remember when the Alaska pipeline went in, tremendous amount of care had to be taken to make sure that that pipeline, which was warm relative to what surrounded it, didn't create a large lake. So it was insulated, and they did a very good job. But now we're talking about everything beginning to thaw, not just where a pipeline is. So houses are beginning to move. People in the Arctic who were living what they thought was very close to the coastline, which might have actually been an ice-covered island, are suddenly beginning to realize that they're on an island. So they're having to be moved a little bit farther inland. And Russia is going to suffer the most from this because Russia has an immense amount of permafrost. They have really not taken much care of it. And all you have to do is drive over the permafrost during a slightly warm day, one vehicle once, and the tire tracks, when you have gone through there, will probably remain as a lake, as linear lakes for decades to come. So it's going to be very hard, particularly in the Russian Arctic, for people to move around. Okay, third thing, catastrophes. There have been tons of extreme events as a consequence, maybe not exclusively, but to a very large degree of this difference in temperature in the Arctic. And it has produced, here's an animation basically showing changes in the shape of the jet stream, and you can see temperatures changing all over the northern hemisphere. Now, that isn't to say that this doesn't happen without Arctic warming, but the shape of the jet stream and the positioning has changed dramatically. The net result is that oceans have warmed. When the oceans warm, you get more moisture in the air masses. The Gulf of Maine is one of the fastest warming areas in the world, ocean areas in the world, and that's the reason that we're getting more precipitation and expect to get more precipitation in the future. It's also the reason that the storms are stronger and the winds are higher, because warm air comes in contact with cold air. Some of the things listed in text under there are either the things that we've worked on or the places we've worked. We're also seeing increased levels of drought because of the shape of the jet stream. California, until recently, has been in tremendous drought because air mass directions that normally feed moisture into it basically have been moved away. Similar to the Mesopotamian example, this year it's been the opposite. But again, it's begun to develop another extreme state. So it's not as if what we were all used to was relatively predictable climate. We're going into much more instability and much bigger changes in state. And as a consequence, in places like California, when you have drought and when the winds, because as the jet stream goes from, for example, north to south, because it has a longer path to go, it speeds up. And even places like Alaska, which you think of as being cold, wet, and damp, are having a tremendous number, along with other parts of the Arctic, a tremendous number of fires. And then finally, the fourth big thing, which I'll just mention again briefly, is climate change, which I believe is certainly if not the major security issue for the remainder of our century. There are tremendous geopolitical implications. This alone, this change from extensive sea ice to not, has opened up all sorts of discussion about where shipping will be, who has rights to the ocean, who has rights to the fish that are going to be in the ocean. For the time being, the central part of the Arctic Ocean, it has been agreed by all of the countries involved in the Arctic Circle, of which we are one, that there will be a moratorium on it, but that won't last more than another 10 years probably. As you know, some countries have put flags down at the bottom. A lot has to do with the bathymetry, where the continental shelf is. There are all sorts of discussion, and this is a reconstruction. It's a bit hard to see immediately, but this is shows you the different routes that vessels can go through the Arctic 2015 versus 2065. And for right now, it's, everybody, Franklin and others always wanted to find the Northwest Passage. The Northwest Passage is the last that's going to open because it has islands enclosing it. The sea ice is relatively thick. It's the Northeast Passage that goes past Russia that is the one that's open right now. And obviously the advantage is a much faster route than going through the Panama Canal. But the question is, when will the center open up, which will probably be in the next 10 or 15 years, not every single year, but for most summers, it will be much more open than usual. And then eventually the line on the left, the red line is the Northwest Passage, and that'll eventually open too. When the Northwest Passage opens up, it's going to be all sorts of exchange with Arctic Canada. And there is, all he knows that he's an American. About 15 years ago, he bought one of the bays in Canada in expectation of the fact that there would eventually be an important port, not for him, but for somebody in the future. So there are all sorts of potential changes. The people who live in these areas their lives have changed dramatically. Where we've most recently worked in Southwest Greenland, the unemployment rate is catastrophic. People are, not that there are a lot of people, but they've lived in these areas for hundreds of years. They have sheep farms, and they live there year round. They're literally just walking away from their houses that they've had for 100 or 200 years because they can't sustain themselves and things are changing so fast. So how might the Arctic impact future climate? It's already had a very dramatic impact. And the answer is it could have an even bigger impact. And that bigger impact has to do with methane. Methane is a greenhouse gas that it's normally emitted by cows, by pipeline leaks, and a variety of other things. It's 30 to 50 times more effective in trapping heat. And one of the largest source of methane on the planet is trapped in the old carbon that's been in the frozen ground, in the permafrost, for hundreds of thousands of years. And as that permafrost begins to melt, it will release methane. And just to show you how easy it is to tap that methane, these people dug a hole in the snow. This comes off the web, and then dropped a match in it. There was no fuel, and it caught fire. So there are going to be, and the lower picture shows you the frozen ground under the frozen organic material. As this happens, which it will, there'll be more and more methane released. How much methane, how fast is not known. It was believed for a long time that the methane release in this area would not be that dramatic. But now we're talking about temperatures of not just 5 degrees centigrade in 5 years, but the expectation is that in the Russian Arctic and other parts of the Arctic, there could be another 2 to 3 degrees, even under normal conditions. And the expectation is that by 2090, just based on CO2, the Arctic will be close to 6 degrees warmer than it is now. So the answer is, if the methane is released at any substantive amount, we will in fact see a rise in the Arctic of another 6 degrees centigrade. So these are the quick take-home messages. Climate can change faster than we ever thought before. As the atmospheric circulation patterns change, they obviously change where heat and moisture go. Small changes can have very large impacts. And whatever you put into the Earth system, in particular in glaciers, when they're melting, it's going to come out. And so we bought into all of this, we did it. And now, of course, we have to be smart about how we deal with it. So one of the things that we do is we've got websites, publicly available software, which on one called Climate Reanalyzer, in which we describe how the instrumental record, what the importance of the instrumental record. I shouldn't say we describe it. A lot of the you can plot for yourself. You can look up your birthday, plot it in there, and see how different the climate was during your birthday than it has been during other years. You can take a commodity, for example, blueberries, and we've done this for the Maine Climate Council report that Governor Mills has sent out. Blueberries like it when it's moist and a little bit warmer. So what's going to happen in the future? Take a look at the current sort of year-to-year production of blueberries. Obviously, it's not all because of climate. There are a lot of other things involved, but it turns out that changes in precipitation, temperature, length of the summer season explain about 20 to 30% of the blueberry yield, which is pretty good thing to know. If you knew 20 to 30, if you could guess what the stock market would do at 20 to 30% probability, you do pretty well. So we've developed the system in Climate Reanalyzer that allows you to take commodities, anything you can make into a time series by day, by year, whatever, and see how it's linked to climate. And then you can look at the climate models that are not produced by us, but that we have in there. And you can see, you can almost project for yourself. So if you were starting a small business, if you decided where you wanted to move to, you could get an idea of what it would be like in the future. And I'll just leave you with that thought. Thank you. Happy to answer any questions.
What about the North Atlantic current getting fresh water from Greenland?
Yes. In fact, one of the things that happens with some of the abrupt climate change events that we have seen in the old records, the past records, is that the atmosphere operates first, but then what's called the conveyor belt or the Gulf Stream, which transports, which our largest export to Europe actually is hot air through the Gulf Stream, and that can in fact slow down, and it will slow down if sufficient amounts of fresh water melt from Greenland and reduce the density of that current so that when it gets in a little bit closer to Europe, it doesn't necessarily dip down exactly. It's not drawn, and as it begins to cool and densify, and if it's drawn down, it drags more heat over to Europe. If that thing starts to slow down, which is what people are concerned about, it'll transport less heat to Europe. It's the Gulf Stream. If it were just a river in the ocean, it would be simple to understand what's going on. But the Gulf Stream is a series of eddies that are all over the place, and how much exchange is occurring in those eddies is unclear. Right now, the melting, it's debatable if the amount of melting that's occurred off Greenland is sufficient to do that much. But without a doubt, once there is a lot more melting, it will have an impact. So what it'll do is create yet another surprise that we weren't necessarily expecting, and that is that you're in a planet, or a planet that is warming will have a place like Europe actually beginning to cool. So thank you for pointing that out. Yes.
Well, with those that have waterfront property, state of Maine, what do you anticipate rising the level of water?
Well, according to the Intergovernmental Panel on Climate Change, the range by 2100 will be about 50 to 90 centimeters. So certainly within the next couple of decades or so, we'll see changes. But so in the short term, in the long term, I wouldn't necessarily build a large city where Castine is right now. But in the short term, it's going to gradually, obviously, rise. But the other thing that's happening that's probably having more deleterious effect is that the strength of the storms is increasing. And they might be becoming more frequent, and they're tracking farther north. And that, of course, this last storm that we had, yeah, big impact. It cut out a lot of the coast. Certainly not something that you should run away and sell your property immediately. But there will be, I think the correct message is that if one were to build something, they should be smart about where it goes, because even 2100 is not the right date to be thinking about. If you start to melt ice sheets, and if you melt all of the Greenland and all of the Antarctic ice sheet and all of the glaciers, sea level would rise about 70 meters, 230 feet. And that's not going to happen, but a lot of it could happen. And we know from the past record, natural times when it was warmer because of other reasons, partially greenhouse gases, but other things, we know that sea level could easily rise 4 to 6 meters. So if you were going to build a large metropolitan area that you expect will last through 2200, 2300, it would be very smart to think about 3 to 6 meters of rise. And it would be very smart for the bridges that we're all replacing around here to think about at least a 1 meter rise, just to be safe. Actually be better if you did a 2 meter rise, but 1 meter would be good. And I know in the bridge that just went from Brooklyn to Sedgwick, they raised it 1 meter.
Yeah, we have some questions coming through on the chat.
Yep.
So the first one is, has your work provided any evidence that the jet stream could weaken over time?
That's a very good question. And because the jet stream has such a circuitous pattern, the answer is that in some places it might weaken, in other places it might strengthen. And Robin Juttenhoff is here, and we're going to start working together. She's working at the Rue Institute and is beginning to learn how to do artificial intelligence. And that's what we want to do. We want to take all of these records that we have access, other people too, but we've made it public. And these records are all sorts of climate variables, temperature, precipitation, et cetera, going back not only daily, but 3 hourly. And we want to see, are there patterns in there when it's naturally warmer, naturally colder. And I think those patterns will help us to understand where the winds will be stronger and weaker. The other thing you can do is go to Climate Reanalyzer, and you can take a look at the correlation function, and you can take a look at the relationship between temperature and wind patterns, and you can actually see what parts of the planet with warmer temperature, the winds speed up and slow down. So it's a great question.
Right, and another one from Peter. Methane oxidizes naturally in a few years. What process could oxidize the increasing methane in the atmosphere?
That's a very good question. It's absolutely
Can you
true.
repeat the question, please?
Can you repeat the question?
Oh,
I can't hear me as well as you.
I think effectively that it has to do with the residence time of greenhouse of CO2 versus methane in the atmosphere, and its availability as something that can trap heat. CO2 has a lifetime in the Earth system and exposure to warming of hundreds of years. Methane less than 50 years. So that's the only good thing about methane. It might be 30 to 50 times more effective in heating, but the levels will dissipate within 50 years for a whole variety of reasons. It's just not going to last as long as CO2.
I'll take the microphone so that they can hear me. I'll take this one.
Okay.
So that way I don't think they see the questions in the chat. Okay, and then the next question is, can you talk a little bit about the climate changes in the Gulf of Maine? Is there relatively less temperature rise closer to the shore due to current of colder water coming down from the north?
That's a good question. I can't say I can answer that specifically. The Gulf of Maine obviously is one of the fastest warming bodies of water. And it is correct that as cold, fresh water makes its way in there, it actually changes the thermal stratification, and it can help to cool at certain times of the year, can help to warm at other times of the year. So I don't know exactly. I can tell you, however, that the pollutants which are coming out of the rivers that enter the Gulf of Maine have a dramatic impact. It's not as bad as it used to be 50 or 100 years ago, but those are, in addition to acidification, in addition to warming, the chemistry of the ocean has become probably more polluted, even though we don't have an awful lot of clothing mills and industry along the coast, mostly because of the way we've conducted agriculture, because of the fact that many places have even small urban centers have paved over so much that there's no place for the surface runoff to actually be absorbed, and it just runs right into the ocean. And obviously we have an awful lot more junk that we have in our lives than people before us had.
And there's another question, so I'll take this back again. And another question that came in through the chat is climate restoration, moving CO2 back below 300 ppm, more important than Paris cutting out emissions? What is ppm?
ppm is it's ppmv. It's parts per million per volume of CO2. And right now we're up to whatever, 420 or something like that from the natural high of 280. Well, you know, there's a lot of debate about how easily you can put CO2 back into the ground. Certainly forestation absolutely is a natural way to do it. We're lucky in Maine because I think 70 to 75% of our CO2 emissions are actually absorbed by our forests. So that makes us look very clean by accident. But nevertheless, and we obviously are a very small population. But in the case of other ways of trapping CO2, you know, there are many attempts at trapping CO2, for example, in Iceland. Much of it is related to putting CO2 back into groundwater and sending it off. Groundwater is only, glaciers comprise about 70% of our fresh water. Groundwater is pretty much most of the rest, probably 20%. So acidifying groundwater is not necessarily a good idea. And it's hard to tell how much energy is actually required to do that. There are a lot of other techniques for trapping CO2. I think it's well worth investing a lot of money in research in these things, but how successful they're actually going to be and whether or not it could happen fast enough is unclear. So Paris Climate Accord, which was originally supposed to, you know, everybody was to agree to a 1.5 degree leveling off by 2100. Everybody now agrees, or they agree, the COP, the meeting of the parties, that 2 degrees centigrade is more likely by 2100 globally. Of course, remember, nobody lives in the global mean. The Arctic certainly doesn't. Their mean is 6 degrees centigrade. But it's a very important thing to do. There were no ways to enforce it. Since that Paris Climate Accord, there have been, I don't know, 5 or 6 more COP meetings. They're certainly trying hard. It's a complicated thing to do, but it's the right thing to do. Just like the right thing to do is to create more forests, to do more research on how to mitigate CO2, but finding ways through laws and policy to do it is extremely important. Whether or not it'll work is unclear. Unfortunately, thus far, not so much. But as people begin to realize what some of the impacts are to them personally, and I would say that the 2 biggest impacts are our health and our wealth. The average Mainer spends 10% of their salary on energy. If you could reduce it by providing cleaner and cheaper energy, that would be much better. Healthcare is a tremendous issue all over the world. So if we could reduce the effects of warming, migration of tick-borne diseases, pollutants, et cetera, we would be healthier, we would save a lot of money, and obviously have a better quality of life. So these are all important things. There's not one thing that should be sidelined. There are plenty of people working on this. There are tons of grassroots organizations, particularly in Maine, working on it. And the more the better. It's great.
And we just had another question come in.
Okay.
So, which is kind of, I like this question. Is there still hope? Sometimes on the news, you see that we're past the point of no return. What are your thoughts on that?
That's an excellent question. And I always hope that somebody will say it at the end of the presentation because I don't want you to go away depressed. Yeah, the answer is that there's plenty of hope. First of all, depends where you live. If you live in the South Pacific Islands, maybe not. If you live in desert regions, maybe not. If you live in Africa, no. Parts of Asia, no. But there is a lot of hope for people who live in more temperate latitudes. There are a lot of new things that are being done. For example, in I think it's Bangladesh, the rice fields are being dramatically impacted by seawater invasion. So people have developed more salt resistant, more salt tolerant rice. There are all sorts of things, for example, Zoom, which means we don't have to travel as much. So I'm very hopeful that we will, in fact, see some very good silver lining responses to all of this. And in that way, yeah, there's a lot of hope. I think for people who are entrepreneurs who want to start not just new businesses, but new ways of living, yeah, there's a lot of incentive for doing it. And I'm very hopeful. I think the latest generation are really beginning to understand this. And we might very well have a much better quality of life in terms of air quality, possibly our health, if we're smart enough to realize what's happening. So it's going to be great. Okay. Oh, any more?
Yep.
Oh, sorry.
There was a follow-up question. For those people in such vulnerable areas, what is their future?
Their future is hard. There's no doubt about it. And we need, certainly that's one of the big things that these COP meetings have been trying to accomplish is how do you help these people who had nothing to do with getting us here? The Arctic is one of the most classic examples. The Pacific Islanders are another classic example. You know, there are 56,000 people live in Greenland who couldn't possibly do anything to impact our climate, and they have almost no emissions. So organizing, as they tried to do at this last meeting in Egypt, organizing wealthier countries to try to support other countries would certainly be a very good thing to do. You know, the Middle East crisis, I think there was something like 30 million refugees. The expectation for climate is 100 to 200 million climate refugees. But if you don't want or can't afford to give them money, you can make money by helping them by developing new ways of doing things. You know, is rather interesting that in our country, we had the best infrastructure in the world in the 1950s, 60s, 70s. Now our infrastructure is old and we need to make a decision about whether or not we'll invest in new infrastructure, ideally a lot of renewable energy. But people who live in many of these remote regions in India, and I've traveled through India, Nepal, Tibet, they don't have telephone lines, they have cell phones. And it's a shame that we didn't, instead of cell towers, buy into satellites, which were available at the same time. We wouldn't even have the cell towers now. So they could make a fast jump that we can't make so easily. It's going to be much harder for us to redo our infrastructure than it is if you have no infrastructure at all to start with it. But it's still going to be hard. They're going to be the people who are hurt the most. Okay. Oh, one more question. Sorry.
What do we do about the great pushback from fossil fuel corporations? It seems that denial of science is a political move that's working. People are willing to pay more for their gas. I mean, they were willing to do that because they don't want to really give up the chance to be able to drive their cars. And the fossil fuel companies know that. I mean, there's a tremendous amount of lack of political will that's not necessarily the people's fault. It's the fact that the denial of science and the pushback is so effective through advertising and misinformation. What comment can you make in regard to any and all of that?
Can you try to summarize that question?
Sure. Yeah. The question was, you know, how do we get the fossil fuel companies to understand that it's important for us to cut fossil fuels, and you know, pragmatically, the only way is if they can figure out another way to make money, and many of them are. If you look at the Arab countries, they are beginning to invest heavily in renewable energy. I think they do realize that they won't have oil forever. But they have enough oil to give to us, and we have enough oil to still make a big mess. One hopes that the market would do it. I don't think it has done it that successfully. There is a lot of misinformation. For example, there are many more people think that they'll lose their jobs, but there are many more people in the solar industry than the coal industry now. If we had offshore wind power in Maine, there are issues with it. But if we had well-planned offshore wind power, as the lobster industry begins to decline, more people with experience in the marine system would be employed. And again, I think the only way you're going to convince people that including the oil companies, that they should do anything is to remind them of people's health and the fact that maybe we're getting smart enough now that we can actually punish people for bad acts that resulted in our poor health and our wealth. And I know for a fact that many of these companies are investing in renewable, but they're also going to probably let it leak out at just, at the rate that they want to. So how do we get around that? Well, in a place like Maine, if we had offshore wind power, we could get off the grid to a large degree from that system. And places like Iceland obviously could do it. Denmark has begun to have a tremendous amount of renewable energy. Denmark doing that isn't going to save the planet, but it's certainly saving them.
And isn't Saudi Arabia investing in hydrogen? So
Yes.
Yeah. So that's nice to see.
It is. But on the other hand, they are, I was invited to Abu Dhabi to give a talk about climate, and I thought that they wanted to know how high sea level would rise and all these other things. And they pretty much knew. And I said, well, what are you going to do about sea level rise? And they said, oh, it's not really a problem for us. Because you see all those islands out there that they had built where they put in high rises, the lower 3 floors are all waterproof. So when the water rises, and the other thing I was told was, how old do you think those buildings are? And I said, I don't know. And they said, those buildings are 5 years old. Another 5 years, they'll be old. We'll build other buildings. And the other thing that they said was that to prevent sea level rise, they would shut off the Straits of Hormuz to keep the ocean from rising. So, which they probably can't do, but those other things they definitely can do. So from their point of view, they have enough money to weather this thing very well. And of course, they have no water other than the desalinization. There's a lot to be learned about desalinization from what they're doing for sure. And in fact, what's the art on Deer Isle? The school? Haystack. They had a freshwater problem, and they have a little desalinator that's just off a raft, and it seems to do fine just for them. So there are plenty of things that can be done, but yeah, it's a problem. Got to chip away at it. I can tell you that in situations in which, for example, people in large industrial environments who are polluting realize that the pollution that they were creating had a direct impact on their family. For example, one of their children with autism, and the possibility that because they were emitting cadmium into the atmosphere had an impact on their own child, did something. Well,
Would you have a question?
No, I want to work on that.
Oh, yeah. All right. So last question, since we're coming up on our end time of 7:30. What would you say to environmentalists that shut down wind farms, solar farms, and the CMP hydro power line from Canada to Massachusetts?
good question. Well, it really depends. A CMP is that line's a different, I think, a different issue in some ways. I think personally, I think the other question is what is Maine getting out of it? It's not clear, but I think it is hard to see solar fields emerging all over the place. When you drive to Augusta, they're all exposed. That's a very stupid way to put up solar panels, in my opinion. We have a lot of land in this state, and all you need to do is leave a really good buffer. So I think, and put solar panels in land that really can't be used for anything else. On MDI, they have a solar farm that they put in that's on their old dump. It's perfect. Why don't we have solar panels on new roofs that are being built? That's what they're doing in Germany. But I guess the choice, and as far as wind farms go offshore, people wouldn't have to look at them onshore, but of course, there's a possibility that they will interfere with migration routes for animals, but why not take 0.5% of what it costs to do that, to actually do all the investigations into where do these animals actually go, put the wind power in the right, in better places, and also set up systems that deflect them by sonar or what else. So you got to give a little bit. Solar and wind are without a doubt the two best things for Maine. Tidal power would be good, but it won't give us a great deal. And we have to make sure that they go in places that are suitable for people. So, but to be opposed to it, to the idea of it, which is what this sounds like sometimes, I think is much too negative. To be opposed to exactly where it's going, that's something else. Okay, well, thank you for your time.